Okay, so these states psi, they're called kets, after Dirac. Dirac introduced this notation. Now, because we have an inner product, that means we have a dual vector space. Then we have the dual of this vector. This is called a bra. Will be given in this form, and it's given by C1 star. So here, this is C1, this is C2. These are complex number. C1 star, psi1, the dual of psi, C2 star, bra of psi2. Okay. So the inner product of two kets, say psi and phi, is denoted by say phi and psi, and it's a complex number, and it has the property that if you take the complex conjugation, then it reverses the order. So let me give you an explicit example of such an inner product and such vectors. So for example, psi could be a two element column vector. So it could be, say, psi1, psi2. Okay, and these are complex valued vectors. Then so this, or I should really let's call it say C1 and C2, and then the bra psi would be given by C1 star, C2 star. Okay, then similarly, phi could be, say, A1, A2, and the bra of phi is A1 star, A2 star. Okay, and then phi, the bra phi and psi ket is going to be just A1 star C1 plus A2 star C2, which is a complex number, right? But see that psi itself is a real number, because according to our assumption, if I take the complex conjugate, it reverses the order, but here it's the same thing. So this is a real number, and not only that, we assume that it is zero or positive. That is what we mean by the positive semi-definite. Okay, here I said positive semi-definite norm.
I see.
So the semi-definite is, and what it means is that this inner product is saturated when this is true. When this inner product is saturated, this means this can only happen if and only if psi is the zero vector. Okay, and we see that all of this is like satisfied by these sort of vectors, right? And this is not a coincidence, because we will see that when we are describing angular momentum and spin, we are actually going to have to deal with finite dimensional vectors. Okay, so I think this is a good point to stop and see if there are any questions.
I don't have any questions, but I did realize that I have some problems with the basics and the terminologies. So I'll have to look into those stuff.
Yeah, look into those stuff and please reach out to me if you have questions, okay?
Would you be able to recommend some of the text or
Yeah, I
lecture
will
notes?
recommend a text for you so that you can learn the basics. And there's a book of mathematics, basic mathematics that you need for undergraduate by Shankar. And I think Nahi has a copy, an electronic copy of that, right, Nahi?
Yeah, I'll send that to Shujosh.
Yeah,
Uh,
and that will have a good section um, on vector space. Okay.
okay, thank you.
Okay. So, any more questions, Rahul? You did not ask a single question in the last course, so I have to. I'm going to call out on you and make sure
Um,
you have questions.
Nothing so far.
Okay, good. You're paying attention, though, right?
Yeah.
Okay, good. All right. So let's see if we can carry on. Now, suppose that psi 1 and psi 2 are orthonormal. What does that mean? So they're orthonormal, meaning they're normalized and orthogonal. Normalization means that this is 1, their norm is 1, and orthogonal means that like this, right? So this is an easy way to, a succinct way to express this is using the Kronecker delta. Okay. So now if I take my state psi, which is a linear combination of psi 1 and psi 2, then from this relationship, it should be obvious that C1 is given by psi 1, the bracket of psi 1 and psi. And C2 is given by the bracket of psi 2 and psi. Now, if psi, this thing, is to be normalized, that is, if I demand this to be 1, then that means that C1 mod squared plus C2 mod squared is equal to 1. So one thing I would suggest to everyone taking this class is that if these statements are not obvious to you, to sit down after class and try to prove every one of these statements. And then if you're not able to discuss it with others, and also reach out to me, okay? Sorry about that. Now, C1 and C2, they have physical significance. So if you make an experiment on the state, on the system which is in the state psi, then the probability that you find the system in the state psi 1 is given by C1 mod squared. And the probability that you find the system in the state psi 2 is given by C2 mod squared. Okay, so those are the physical interpretation of these coefficients. But of course, for that, this needs to be normalized. If it is not normalized, then these probabilities won't be absolute probability, they'll be relative probabilities. So implicit in all of this is that if you have a state and you rescale this state by a complex constant, then you get the same state, right? You're just rescaling the probabilities there. So that's why often you will see that they will say that the physical state of a system is represented by a ray in Hilbert space. By ray, they mean that that if you have two states which are proportional to each other, then in terms of physical significance, they are equivalent. They are identified. Okay, so this is what it means. Okay, so the dimensionality of the Hilbert space, as we shall see, will depend on the system. So if the system, so often we will deal with infinite dimensional Hilbert spaces. But for now, let's just take an orthonormal basis for Hilbert space to be ket of psi I, where I goes from 1 to n. So n can be infinite. So any arbitrary state of your system can be expressed as a linear combination of these basis states. So that should be an I. And the sum of probabilities being 1 is expressed by the statement where all the a's, all the modulus of a squared sum up to 1. Okay, so in case where n is infinite, when n is infinite, we have to assume that this sum converges. Okay, when n is not infinite, of course, it will converge automatically.